So in the last module, we started looking at the vector description of rotational motion. And we came up with a vector description of position, which described the object moving in a circle as a function of time. It looked like this. And then by differentiating, we were able to come up with a expression for the velocity as a function of time. And we noted the relationships between them. They're always perpendicular, as well as the speed, or the tangential velocity, is related to the angular velocity times the radius of the circle. Next, we want to take a look at the acceleration, a as a function of t, which is given by our fundamental definition to be the derivative of the velocity as a function of time. Okay, so this now gives us good practice with our rules of differentiation, because now we have the product rule, the sum rule, and the chain rule all at the same time. So I want to differentiate this object here. Sine theta is a function of time. I hat plus r omega, which is a function of time, times cosine theta, which is a function of time, j. So we want to differentiate this whole thing. Okay. Well, we'll just take it one step at a time. So first, here's I have two functions of time, so I'm going to use the product rule, differentiate this times the sine, and then differentiate sine times the omega. So the omega function. So that gives us negative r times the differentiating omega t times sine theta, and I hat is just a constant, so just it comes along with us. And then we have the derivative of sine, so minus r omega t. Now this we need the chain rule, and so that gives us cosine theta of t times, again, the derivative of theta, chain rule. And again, this is I hat. So that's our two terms for using the product rule for this. And now we have to do this term, and it becomes a similar expression. So first we differentiate the first part using the product rule, r times the derivative of omega t, then cosine theta j. And now we need to differentiate the second part, and so we'll pick up the derivative of cosine theta is negative sine theta, so we're going to get a negative r omega as a function of t sine theta t. But again, chain rule means we have to have another derivative of theta with respect to t, j. All right. So there's some good derivative practice for us. So what are we going to do with this thing? Okay. Well, the first thing to recognize is, again, these here is another factor of angular velocity, the derivative of the theta function with respect to time. And also, if you recall from before, the derivative of angular velocity is our angular acceleration, which we call alpha. And it is also a function, it could be also a function of time. Okay, so we can substitute that, and now we'd like to sort of combine these terms. Now, it would be reasonable to think that we would combine them into x components and y components. But I'm not going to do that. I'm going to arrange them in a different way. And we'll see how that works. I'm going to combine these two terms together and these two terms together. And so let's see how that would work. So this is still our angular acceleration. Our regular, or this is the acceleration. Okay. And so if I combine these two terms, they each have a factor of r and alpha. And so I can pull that out. And so I have r alpha as a function of t times this first term has a negative sign, so negative sine theta of t I hat, and since they're, one's I hat and j hat, I can't combine those. So plus, and this has then a positive cosine theta of t j hat. So that's the first term. Looks like I'm going up a little bit. I'm losing my parallel here. So that's the first term. And now we'll look at the second term, which combines these two. So they each have a negative r omega squared. There's another omega here. So I can factor those out. And so I get minus r omega, which is a function of t, squared, times and I pulled out the negative as well, so this is cosine theta of t plus sine theta of t. Oh, sorry, this is I hat, j hat. Okay, so why would I want to organize the terms this way? And what makes this very interesting, and a great way to do it, is because this right here is a unit vector, and not just any unit vector. It is the unit vector of the velocity function. And this is also a unit vector. It is the unit vector of the position function of time. So now we can rewrite our acceleration in this way. So our acceleration as a function of time is equal to r times our angular acceleration alpha that points it points along the direction either forward or against, but along the line of the velocity vector, minus r omega squared, which is a function of time, times the position vector, unit vector. So I've broken my acceleration into two parts, one along the line of the velocity vector and the other along the line of the position vector. And so let's take a look at this for a minute. Let's get a graph here and see what this means. So I have here my circle, I have an axis. And if I have some particle here, and it's going to have, let's say, my velocity is in that direction. I have my radius, which is always pointing this way. So this is my radius function. Obviously, that's the radius direction. The radius vector points to that part. They're always perpendicular. And now I have an acceleration vector. Now it has a component here that points along the line of the velocity vector. Now it can point either way. It can point in the same direction or the opposite direction, but it points along the line of the velocity vector. This alpha function can be positive or negative. But look at, for this part over here, r is the magnitude of the radius vector. It is always positive. Omega squared is always positive because it's squared. And so because of this minus sign, this term always points in the opposite direction of the radius vector. And so that is interesting. While this can go in either direction, this always points towards the center of the circle. Okay, so now I want to look in particular at these magnitudes. What exactly are they doing? Well, what this magnitude is doing of the acceleration, this is changing the speed of the object. This is either speeding up or slowing down the particle. It is always acting in the same or the opposite direction of the velocity. So to the degree that this is positive or negative, and what the sign of the velocity is, it is changing the speed of the particle. While this term here is what is changing the direction of the particle. As the particle moves from, well, let's see. Let's say the particle moves from here to here. So once the velocity was in that direction, now the velocity is in this direction, and the radius is here. And it may have been sped up or slowing down depending on how it's changing the speed, but it has definitely also changed direction. And it is this acceleration here that always points towards the center of the circle that is changing that direction. And so, again, just like the position vector is always pointing radially along the radius, this term of the acceleration is always pointing along the radius. It is just pointing toward the center of the circle instead of to the outside of the circle. Okay, so because these terms are so important, they get their own names and, in fact, their own symbols. So this first term, which is a sub t, a function of t, it is called the tangential, and it's equal to r alpha t, is the tangential acceleration. And this other term, which is called a sub c, and it is equal to r omega squared, function of time, is called the centripetal acceleration. Centripetal means center-seeking. It's supposed to remind us that this acceleration always points towards the center of the circle. It's this component of the acceleration. And so this is centripetal acceleration. And so we now have essentially 4 accelerations to keep track of. You can't forget that alpha of t, which is the time derivative of the angular velocity, is the angular acceleration. And of course, we can't forget this, which is just the acceleration. It's the acceleration. And it's given by the time derivative of the velocity. I will say that centripetal acceleration is sometimes called radial acceleration. because just like the tangential acceleration always has a direction tangent to the surface, the centripetal or radial acceleration always points along the radius of the circle. Okay. And so, just in case you run into that term as well. So we have the acceleration, which is broken up into a tangential component and a radial component that have two different purposes to change the speed and direction of the particle. So now you can see sort of where the tangential velocity came from, which is equal to r times the angular velocity. This is the tangential velocity. It is the quantity that is changed by the tangential acceleration. And then, of course, there's the position vector itself, which is just the radius times the radial component. So the radius always points radially. The position function always points radially. The velocity always points tangentially. And then the acceleration has both a radial and a tangential component. And the tangential component changes the speed while the radial component changes the direction. And now we have these relationships between the various components that we can use to solve these rotational motion problems.